Michael Kiessling, who will talk about joint work with undergrad Renna Yi, about Hilbert's monkey saddle and other curiosities. All 3-point particles, Riesz Equilibrium, etc. Thanks so much for coming. Please don't occupy this set because the collaborator is coming late with the wheel. Reminding you, thanks so much for coming. There are absolutely no electronic devices are allowed. But on the other hand, we're guaranteed to finish in 48 minutes. Thank you.
Okay, thank you, Dawn. Thank you very much. Indeed, this is a summer undergraduate research project that I'm reporting on. And undergraduate is Renna Yi. She majored in physics and is currently majoring in mathematics. And she is commuting from Livingston campus over. So that may take a little bit, that's why she's not here yet. And, okay, so the title is...
sorry, please, this last row. Sit anywhere.
Sit here, that's fine. Yeah. Just the last row is empty. Okay, so that's the title as you can all read yourself. And so let me first begin with the motivation. And the motivation is the optimal n-particle configurations on the little n-dimensional sphere. No? So there's capital N and little n here. And so what I mean is you pick n distinct points in R to the n plus 1, little n. And, but they have all Euclidean length 1. Okay. Take any pair, say pi and pj, and you define the Euclidean distance in R super n plus 1 and call that Rij for this pair. And it has to be positive. So you don't want particles right now on top of each other when I talk about configuration. And then you assign each pair a Riesz S energy. So this is the definition when S is not 0, right? And essentially it's of course just a power law. But the reason it's written like that is because then you can take the limit as s goes to 0 and you get log of 1 over r. So you don't need to chop it into pieces. And in fact, I just want to draw a small picture there that you get an idea of how this family looks. Okay, so here I'm plotting v sub s as a function of r, and somewhere here you plot r, the pair distance, and then let's say here is 1 and here is 1, and there's a straight line going right through, and that would be s equals negative 1. Okay, that's just a straight line down. And the interesting thing is that all the curves meet at that point, and they are also, the family is monotonically ordered in S. So if S is bigger than negative 1, so you have a kind of singularity now here. So at the beginning, it still is finite, but it comes with an infinite slope down, touches this straight line at 1, and goes to infinity, but in a convex manner. So this is negative 1 less than s less than 0. If s is 0, you have the log, right? So it goes to infinity, and when r goes to 0, but also still goes to infinity, just much slower. All right. So if s is bigger than 0, of course, it also goes to infinity, touches at 1, but now tapers off eventually asymptotic to a constant. On the other hand, if s is less than negative 1, then you come out with a nice 0 slope, touch here, and go down. Let's say, for instance, s is negative 2, and so on and so on. So this is a monotonic family of pair interactions, and they are all repulsive. Each pair interaction is such that the further apart two particles are, the lower is the pair energy. All right. So this is just so that you know how they look. So now you take an n-point configuration, capital N, and you define the average pair energy. You have in total n choose 2 pairs, right? So you sum over all distinct pairs, and of course what you are summing up is the pair energies in the configuration, you divide by the number of pairs, and you call that the average pair energy of an n-point configuration. Moreover, you define the optimal average S-Ries pair energy of an n-point particle system by asking what is the infimum of this expression over all possible configurations, and you call that little v sub s of capital N. Okay? So far, all motivation. Next, why are we doing this? Well, first of all, it's nice and beautiful and interesting, but it's also very useful. So here, this is from Rob Womersley's webpage. This is a fantastic webpage of Womersley at University of New South Wales in Sydney, and this is about 100 points. This is then a triangulation. It means you just connect any 2 points and you get this triangular shape. And these are Voronoi cells. Let's not worry about those too much, but here you see a picture taken by NASA of a familiar place in the universe. And of course, you see in particular certain weather patterns, right? So this looks like quite some vortex, no? So a little bit mushroomy-like. And so now suppose you want to simulate large-scale weather pattern. On that scale, the thickness of the Earth's atmosphere where weather happens is, let's say, not more than 20 kilometers, and on the scale of the radius, that's very small, right? So in first approximation, you may formulate that as a simulation of a two-dimensional fluid flow. But how do you simulate a two-dimensional fluid flow? Can you sit there? Not in the last row, please. Yeah, in the one row further.
The collaborator is supposed to come.
We need space there.
Yes.
Right? So how do you simulate? You triangulate, you discretize. You triangulate the object you are interested in, the domain. And here is such a triangulation. Now the point, of course, is you have to question where should you put the triangulation points. And in order, here's my collaborator coming in. Hi there. We have made room right there. You can go all the way to the middle. So that is Renna Yi and her mom. And so the interesting thing is that for certain algorithms that numerical people use, the answer where should you put your triangulation points is optimize the pair energy. Find the optimal energy configuration for a certain S. Depends on what type of question you ask. And so there is a certain amount of interest to find the optimum configuration for many, many points. And what do we know about those? Well, if the parameter S is bigger or equal than 2, then an optimizer actually exists always. So that means give it a star here, and so you stick in that configuration, and that gives you what you computed or what you know existed as the infimum. But they are not unique. Even if you factor out the rotations and you factor out the permutations, there may be more than one optimizer. But what is much more of a problem, and that makes it really exciting and hard, is that that's purely empirical, that the number of local energy minimizing configurations, which are not necessarily optimal, seems to grow exponentially with the number of points. But nobody, as far as I know, was even able to prove upper and lower bounds which are exponential. So this is an interesting, hard problem. Also, the question would be, if it's true, really, what is the significance of the parameter gamma there? But in any case, the point is that since there's no surefire way to compute this optimizer, people use, well, random algorithms partly, or start with a random configuration and then minimize according to some gradient flow or whatever. And so that's where experimental math comes in, and that's the title, of course, of this seminar in general. But what is known is for large n, there is an expansion which seems asymptotic for a few orders. So this is the optimal average pair energy. I multiply by the number of pairs because people usually write the total energy. So, and this is on the sphere. That means, wait a second, here am I, right? Dimension m of the sphere is 2. And I choose for the parameter S0, that's the logarithmic pair interaction. And this is your expansion. So this here is so simple, even I can prove this. This here I can give you a plausibility argument for. This I cannot prove, right? But it was proven. The first three terms have been rigorously proven, and this is conjectured. Here are the coefficients A, B, and C. D, well, yeah, numerical work is there. And, all right, but as I said, this is a hard problem to get to the minimizer, because you more likely, when you start with a random search, to end up in a local minimizer, which is not optimal. So, and then Steve Smale proposed, when he was asked to come up with a list of problems worthy of the attention of mathematicians in the 21st century, problem number 7 is this. For each n, can one find a configuration, you see there is not the star, it's not necessarily the optimizer, a configuration on S2, such that the discrepancy of the average pair energy of this configuration from the optimum, whatever it is, differs by not more, essentially, than this term. But of course here, this is the average energy, so I divide by n squared, or n times n minus 1. And the d here is not the little d necessarily. He said, I don't care about that constant, but he cares about this. So, and this is pretty small. That means he wants to get very close, and he says, maybe this is good enough for the purpose of finding good configuration. And, however, he wants that in polynomially many steps in n. Right? Okay, but what do we know about the parameter regime S less than 2? Actually, this is a typo, it should be less than minus 2 here. Not less than 2. Less than minus 2. Here is also minus 2. Björk in the 50s proved that in this case there is no optimizer as a configuration unless n is 2. But thing of particles, they coagulate onto not more than 3 points, A, B, and C. And so therefore this is not a configuration anymore, but we can speak of a particle arrangement. And here's the second picture, because for some strange reason, the paper, the preprint that we have, you see also alpha, beta, and gamma in here, and for some reason that doesn't show up here in the BMO file. I don't know why. It's the same picture. So let me just draw this unit circle here and some triangle in here. Okay, so here is alpha, here is beta, and the angle up here is gamma, and then you have A, B, and C, and the side length is A, B, and C. Okay. All right, so 3 points are inevitably, of course, on a great circle, even if you start the problem on S to the little n. I mean, optimizing points, and so we speak of an optimal n-particle arrangement, not a configuration. It's a degenerate configuration. Now, interesting, if the number of particles is an even number, then the optimizer consists of a configuration which is antipodal, and half of the number of particles is sitting in each of the 2 antipodal points. But when the number of particles is odd, the story becomes more interesting. Of course, if one particle is odd, but that's not interesting. So the minimum you have to do is to take 3 particles, and that's where the project starts. Well, also Renna started to look into. So if you have only 3 particles, then of course in general you have a configuration now with distributing the 3 particles onto 3 points. And so the average pair energy then can be expressed just in terms of the side lengths. You stick here the Rij's are A, B, C now. And the angles show up, alpha, beta, gamma, so you can express this uniquely in terms of the angles. So this is now the average pair energy as a function of alpha, beta, gamma. And of course you ask for what is the infimum, but the point is, with 3 particles, presumably you can do more and figure out not only the infimum or maybe a minimum, but also a maximum and maximizers, local and absolute and saddle points. So why don't we try to understand the whole thing? So you compactify it also by defining that what you mean by the pair energy when the distance between 2 particles is 0. Well, it's just this when s is less than 0 and it's infinite when it's positive. So now you have particles sitting on top of each other for all s. And you find all critical points, and now come a number of theorems, and later will come a number of pictures. So the first thing is that the optimizers were sorted out by Neratini, Achille Neratini, Johan Brauchon, and myself. So in 2014 we have a paper, and so the interesting thing is that there is a phase transition. What would you expect to be the optimizer with 3 particles that repel each other? Well, presumably the equilateral triangle. And that is true when s is large enough. But when s is reaching this critical value, the log of 4/9 divided by the log of 4/3, there is a phase transition that happens, and the optimizer switches to an antipodal configuration with 1 particle, let's say, at the north pole and 2 particles at the south pole. That's a discontinuous jump in configurations or arrangement space. But at s equals 3, these 2 configurations/arrangements have the same energy, right? So it's a first order phase transition in the name of thermodynamics, if you want. And that concerns the optimizer. But what about everything else? So, maximizers. Now, from here on, everything is from the summer research project. So the maximizers, well, what could be the absolute maximizers? Well, all 3 particles are sitting on top of each other, right? So that's the absolute maximum energy. Yes, sure, of course, that's a universal maximizer. But also, if 2 particles are sitting on top of each other and the other one elsewhere, namely antipodal, that will be a relative maximizer when s is large enough. And moreover, interestingly, the equilateral configuration is also a relative maximizer when s is less than -4. Now it gets a little bit denser, but now we talk about proper equilibria. Proper equilibria are if the force is defined between 2 particles, but without having necessarily a particle sitting on top of each other, but they may. If s is less than -1, sorry, then 2 particles sitting on top of each other are in a force equilibrium which is proper. And so this is listing all possible equilibria. Of course, here alpha, beta, gamma, when gamma is pi in this picture, right, then all 3 particles are sitting on top of each other. That's one equilibrium. That's the absolute maximizer. But if gamma is 0, right, and you have pi half for alpha and beta, then 1 particle is at the north pole, and these 2 guys are sitting both at the south pole, so it's another degenerate configuration. It's also proper equilibrium. And of course, the equilateral configuration, all angles are the same, pi/3, is a proper Riesz equilibrium, and these are actually universal equilibria because they don't depend really on s. If you allow the pseudo-equilibrium when the force is not a proper force, but has a tip, like up there. And but interestingly, and that is somewhat unexpected intuitively, there are also isosceles triangular proper Riesz equilibria which are not equilateral, they're isosceles. And there are 2 continuous open families of isosceles triangular proper Riesz equilibria which are not equilateral and not degenerate. 2 families. And that list exhausts all the equilibria that there are that are proper. And And part of the way to show it is that any equilibrium must be, even in a degenerate sense, an isosceles arrangement. So there are no such things like non-isosceles triangular equilibria. Pseudo-equilibria are those, as I said, when the force is not defined in a proper sense, but you define them when particles are sitting on top of each other and a small variation leads to either an increase or decrease of energy. And there is only the total collapsed configuration and the antipodal configuration, the 1-2 configuration, that are pseudo-equilibria. There are no others. And that happens only when you actually have a non-proper force. That means when S is bigger than -1. But what about saddle points? Right? I said there are two families of proper isosceles triangular configurations, and here is where they exist. Right? This is everything except S equals -4. S equals -4 is still an equilateral configuration. So that is everything but S equals -4, but here you restrict to S less than -2. Right? For this parameter range, and of course there is now one parameter range where S is less than -4, and the other parameter range is S then bigger than -4, but less than -2. These are the two families where you have isosceles equilibria, which are not equilateral or triangular. But when you take the closure, then the equilateral triangular configuration is part of it, namely when S is -4 in the closure. And the antipodal arrangement sits at S equals -2, right? And so these are giving you saddle points. In addition, the antipodal arrangement is a saddle point even all the way up to 0. And here is once again in more detail the description of these isosceles families. I already mentioned one goes from S starting at -infinity going up to -4, and that interpolates continuously and monotonically between a right triangular configuration, that means gamma is pi-half, gamma is the angle upstairs, and it converges when S goes to -infinity. And the equilateral configuration, gamma is pi-third, happens when S is -4. So that's the other endpoint of one continuous family. To the right of S is -4, but to the left of S equals -2, there is another continuous family of isosceles triangular Riesz force equilibria. And that also interpolates continuously between the equilateral configuration at S equals -4 and the antipodal arrangement. Continuation. We can work out the asymptotics. So this is when S goes to -infinity, right? So gamma converges to pi-half. How does the neighborhood look like? It looks like that. Pi-half minus square root of 2 to the 1 plus S. What about the neighborhood of S equals 4, -4, where at S equals -4 you have along these families, you converge to the equilateral configuration? Well, that is a Taylor expansion, pi-third, and then comes a linear term in S, and plus higher order powers. So, of course, you Taylor expand around S equals -4, that's why you see this one. And here's the first surprise. It comes here when you approach S equals -2 from the left. So the isosceles triangular configuration converges to an antipodal degenerate configuration, but look how it does so. Antipodal means gamma is 0. This is collapsed here, and you have one here and 2 particles down there. But look, this is 2 to the 1 over the difference of S and 2. Okay? So this is a function we usually cook up in calculus courses when we try to explain to students a C-infinity function, right, which has a Taylor series, and the Taylor series converges, but it converges back to the function only at one point, which is normally cooked up. Here it comes for free out of the behavior of that bifurcation branch. So that was a surprise that one of those cooked up examples actually show up naturally here. Normally it's e to the 1 over x squared that we say when x is not 0, and it's 0 when e to the minus 1, whatever. So, good, here's a picture. Pictures say more than 1,000 words. So what is plotted up here is gamma, this upper angle of otherwise always isosceles configurations, and the horizontal lines are giving you the universal equilibria, whether proper or pseudo. Right? So this is the all three particles sitting on top of each other. This is the antipodal configuration, one particle in the north and two particles in the south pole. This here is the equilateral configuration. Here, this branch is consisting of isosceles equilibria, and that one also. In the middle here is the equilateral one, which is universal. The other parts here, the bent parts, are the non-universal equilibria because they depend on S. And this non-analytical bifurcation is here, and there is an analytical bifurcation there. The color code, which didn't come out exactly right here again, so in the paper it's slightly better. So the colors here are okay, but this here should be light blue and dark blue. No? So this is the absolute minimum in terms of the Riesz energy here also. And here's the phase transition between the equilateral configuration and the collapsed configuration, which is antipodal. Yellow is a local minimum, which is not absolutely minimizing. Green is saddle points. These are saddle points in energy. Light blue is a local maximum, which is not a global maximum. And dark blue, which is written in big maximum, is this one. That's the absolute maximizer. That's the complete characterization of those three-point equilibria when S is less than minus 1. If you continue to the right, there is no such curve behavior anymore. Everything is just horizontal lines, and this stays all the way up to S equals infinity, the global minimizer. And these are the only other pseudo-equilibria. This turns into a local maximizer, and this remains a global maximizer. But, of course, I also promised that we are having the Hilbert monkey saddle. So where's the Hilbert monkey saddle? Well, coming up. First, let's look at the energy as a function of gamma for all possible isosceles configurations. Right? Not just equilibria, all possible isosceles triangles, energy as a function of gamma parameterized by S. And that paves the road a little bit. That is this picture. Right, so now it's written U because I subtract some terms so that it fits nicer in there. And S is the parameter, parameterizing the curve. Here is the list of parameter values. You see also blue and green color here. Green is S equals -4, that is this curve. And blue is, of course, the critical curve where the phase transition happens. But what is plotted is energy versus the angle gamma. Okay? And the equilateral configuration sits at pi-3rd. Gamma equals pi-3rd. And you see this is always either a minimum, saddle point, I mean it's an inflection point, or a local maximum. So at gamma pi-3rd there is always an equilibrium. Moreover, there is always a maximum at gamma equals pi, the absolute maximum. That is all three particles sitting on top of each other. Moreover, there is always at gamma equals 0, no, this is the, what is that? Pi. Yes, gamma equals 0, sure. Collapsed. This is the antipodal configuration. Interestingly, in this plot, it always has the same energy, but it is a maximum here, and then it turns into a minimum. But what happens is, see, when you make S smaller and smaller, this is large S, and then S gets smaller and smaller when you go up. So this, what was an absolute maximum, becomes here also absolute, and suddenly absolute minimum, relative minimum, inflection point, relative maximum. I think now I got it. Right over my lips. And there's an interesting phenomenon. See, there's a min here, but that min moves to the